Welcome, fellow curious mind. Pull up a chair. You probably already know the sun is this, you know, volatile, churning nuclear reactor.
Yeah, it is definitely not quiet up there.
Right. And you've likely seen the recent headlines about auroras pushing unusually far south.
They're beautiful, but they definitely represent something much more intense happening behind the scenes.
Exactly. So today, we're tailoring a deep dive entirely for you that looks far past those pretty lights in the night sky.
We are getting right into the mechanics of it.
We really are. We're diving straight into the hardcore engineering vulnerabilities of our highly interconnected world. And our guide for this journey is, it's a phenomenal, highly detailed report by the Royal Academy of Engineering.
Right, it's titled Extreme Space Weather, Impacts on Engineered Systems and Infrastructure.
Yeah, that's the one.
It is just a remarkable piece of analysis. I mean, it takes a phenomenon that originates 93 million miles away and literally maps its physical consequences right down to the microscopic circuitry.
The circuitry inside the satellites you rely on every single day.
Exactly. And even the massive steel transformers that are currently powering the room you're sitting in.
It's wild to think about. So the mission of this deep dive is to, shortcut your way to understanding exactly how a solar superstorm works mechanically.
Right. What it could actually do to the infrastructure holding modern society together.
And how engineers around the world are furiously working to build resilience against a threat we frankly cannot control.
We just have to weather it.
Okay, let's unpack this. To really grasp the scale of the threat, we have to trace the anatomy of a superstorm.
Because it's a very specific sequence of events.
Right, because you already understand that space weather isn't about wind and rain. We're dealing with high-energy radiation and magnetized plasma.
It's a completely different beast.
So I want to understand the sequence. How does a bad forecast turn into a full-blown eruption?
Well, the timeline unfolds in 4 very distinct phases, and it begins directly on the solar disk.
Okay, phase 1.
Right. Forecasters monitored the development of complex sunspot groups. Think of these as regions of intensely twisted magnetic fields.
Like tightly coiled springs.
Exactly like tightly coiled springs. They're the early warning signs. And when the tension in those magnetic fields becomes just too great, they undergo a violent realignment.
They just snap.
They snap. And that snap is phase 2, the solar flare.
And because a solar flare is an explosive eruption of pure energy like X-rays, optical light, radio waves, it travels at the speed of light.
Right, so by the time our telescopes actually see the flash, the impact is already here.
Wow, so there's zero lead time for that part.
It is instantaneous for all practical purposes. 8 minutes after the eruption, that radiation hits the day side of the Earth.
Just baking the upper atmosphere.
It ionizes the upper atmosphere completely, and that can immediately degrade or even totally black out high-frequency radio communications.
Across the entire sunlit hemisphere of the globe.
Across the entire day side, yes. But the flare is really just the opening punch. Phase 3 follows closely behind.
Bringing the solar energetic particles, the SEP.
The SEPs, these are the heavy hitters, highly accelerated protons and heavy ions.
Like microscopic cannonballs flying through space.
That is the perfect way to describe them. These particles are accelerated by the shock wave of the eruption itself.
And they arrive pretty quickly, right?
Yeah, they arrive in near-Earth space minutes or sometimes hours after the initial flare. And they bathe the Earth's orbital environment in high-energy radiation for hours or sometimes even days.
Which is a severe threat to astronauts.
A massive threat to astronauts and to the electronics on any spacecraft operating above our atmosphere.
Which sets the perfect stage for phase 4.
Yeah.
I mean, we've had the light, we've had the radiation, and now we get the actual mass.
The coronal mass ejection, the CME.
So what exactly is a CME?
A CME is a colossal cloud of plasma. We are talking billions of tons of solar material, all entangled with its own localized magnetic field.
It's blasted out into the solar system.
Blasted out. But because this cloud has physical mass, it takes time to cross that 93 million mile void.
It's not moving at the speed of light anymore.
Nowhere near it. Historically, extreme CMEs are launched at speeds exceeding 800 kilometers per second.
Which is still insanely fast.
Oh, absolutely. Sometimes they approach 1,900 kilometers per second. That gives us a transit time ranging from anywhere from 15 to 72 hours before it physically collides with the Earth.
But the arrival time isn't the primary factor in whether we get a manageable light show or a global infrastructure catastrophe.
No, it's not. The speed matters, but it really all comes down to a very specific magnetic orientation.
The magnetic field of the cloud itself,
Exactly. The orientation is the defining variable here. The Earth is protected by its own natural magnetic shield, the magnetosphere.
which generally points northward at the equator.
Right. So if the incoming CME cloud happens to have an embedded magnetic field that is also pointing northward, the two fields basically repel each other.
They clash.
They clash, and the plasma largely just deflects right around the planet.
But if the CME's magnetic field is pointing southward,
Then we face a completely different scenario.
it essentially acts like a key, fitting perfectly into a lock, peeling back our defenses.
That phenomenon is called magnetic reconnection. The southward solar field links directly with our northward terrestrial field.
Opening the floodgates.
It opens a massive doorway. It allows enormous amounts of solar wind energy to pour directly into the Earth's magnetic tail.
And that energy doesn't just flow smoothly, does it?
Not at all. It builds up tension in the magnetotail until it reaches a breaking point. Then it releases explosively back toward the night side of the Earth.
In those violent pulses.
Yes, violent 1 to 2 hour pulses known as substorms. So an extreme geomagnetic event is actually a series of explosive, localized pulses violently shaking our planet's magnetic field.
You know, understanding those physical mechanics makes the historical record of these storms so much more visceral.
It really grounds it.
Yeah, because we aren't just theorizing about these impacts, we have a solid track record. For you, the listener, the absolute gold standard of solar superstorms is the Carrington Event.
September 1859.
Right. The CME from that storm was so incredibly fast, it arrived in just 17.6 hours.
Which is blistering.
And the induced electrical currents in the ground were so powerful, they literally set telegraph systems on fire.
Operators were getting electric shocks straight from their own equipment.
Yeah. I read that some of them actually disconnected their batteries and just used the ambient auroral current to transmit messages.
Which is a fascinating historical quirk, honestly. But the infrastructure we rely on today is vastly more fragile and infinitely more interconnected than the Victorian telegraph network.
Definitely. And we've seen flashes of that modern vulnerability, too.
Yeah.
Like in May 1921.
The Swedish telephone exchange fire.
Exactly. A severe solar storm induced currents that started a fire right in the exchange. There was a certain dry irony in our communication networks, literally burning themselves down with their own physical infrastructure.
And then we have the near miss of August 1972.
Oh, that one is terrifying. That holds the record for the fastest CME transit time ever recorded.
A blistering 14.6 hours.
And it happened right between the Apollo 16 and Apollo 17 lunar missions.
That timing is incredible. Had astronauts been walking on the moon during that event, the radiation dose would have been absolutely lethal.
But for the Earth itself, because the magnetic field of that specific CME happened to be pointing north, it basically just bounced off our magnetosphere.
It was the perfect paradigm of a bullet grazing us. We absorbed the radiation hit in orbit, but we avoided the catastrophic geomagnetic shock on the ground.
In March 1989, though, the orientation wasn't in our favor.
No, it's pointing south.
That storm hit the Hydro-Quebec power grid in Canada. And within 92 seconds, just 92 seconds, the entire provincial grid collapsed.
6 million people were plunged into freezing darkness for 9 hours.
The socioeconomic disruption was massive. And up in orbit, the atmospheric drag changed so rapidly that the military completely lost track of over 1,000 objects on their radar grids.
For almost a week, they just didn't know where the satellites were.
So, looking at that history, you really have to wonder about the statistical probability of a Carrington-level event happening today. The report actually cites a major study estimating a 12% risk per decade.
If we connect this to the bigger picture, we have to be incredibly careful about how we interpret the math of rare hazards.
How so?
Well, you'll frequently hear commentators claim that we are mathematically overdue for a superstorm because it's been over 160 years since 1859.
Right, like the clock is ticking.
Exactly, but random systems have no memory. The universe isn't keeping a tally to balance the books.
The gambler's fallacy.
Yes. The probability of a storm happening this week is the exact same as it was last week. Flipping a coin and getting 5 heads in a row doesn't make a tails any more likely on the 6th flip.
Right. The risk of the event happening remains static, but our exposure to that risk accumulates over time.
Precisely. The probability compounds over the lifetime of the system you are operating. The mathematics outlined in the report dictate that any engineered system designed to last more than 8.25 years has a greater than 10% chance of experiencing a severe space weather event.
During its operational lifetime.
Right. And when you consider that we build national power grids and satellite constellations meant to operate for decades, an extreme solar storm is no longer a hypothetical, distant risk.
It's a baked-in engineering certainty.
It absolutely is.
Here's where it gets really interesting. How does a storm that is entirely magnetic, happening millions of miles away in space, manage to physically melt a 400-ton steel transformer bolted to the ground here on Earth?
It all comes down to geomagnetically induced currents.
GICs.
GICs. During a worst-case scenario storm, the Earth's magnetic field fluctuates wildly. We are talking variations of up to 5,000 nanotesla per minute.
That's a massive shift.
It is, and that rapid magnetic fluctuation acts like a massive invisible generator, inducing a powerful electric field directly into the surface of the ground.
Which then finds its way into the grid.
Right. The physics of this failure mode are brilliant, even if they are highly destructive. The key to understanding this is a phenomenon known as half-cycle saturation.
Because our grids use alternating current, right, AC?
Yes. Our modern power grids operate on alternating current, where the electrical current reverses direction dozens of times a second. But the current induced in the ground by space weather fluctuates on a timescale of minutes.
So compared to the rapid hum of the AC grid, this storm current essentially acts as a quasi-direct current.
A steady DC push. And transformers are fundamentally designed for AC sine waves, not a steady push of DC.
So what happens when that DC current hits the transformer?
When this rogue DC current travels up through the grounding wires and enters the transformer, it violently shifts the magnetic core off its operational center.
It magnetizes it in one direction.
It magnetizes the steel core in one specific polarity. This physically pushes the alternating magnetic flux completely out of the engineered steel core.
And that magnetic flux has to go somewhere.
Exactly. It enters the surrounding structural components and the insulating cooling oil inside the transformer.
Which causes heating.
Immediate, rapid, intense heating. The oil begins to bubble, off-gassing explosive hydrogen.
And the grid itself starts to destabilize even before the transformer physically melts down.
Because of that core saturation, the transformer suddenly starts consuming massive amounts of reactive power.
Reactive power being the background pressure of the grid.
Basically, yes. It's the electrical pressure that keeps the whole alternating current grid flowing synchronously. When these massive transformers suddenly suck that pressure out of the system, you get a cascading voltage collapse.
The safety relays trip.
The line shut down and the blackout spreads rapidly.
To ground this reality for you, the report lays out exactly what this means for a highly developed infrastructure like the United Kingdom. If a 1 in 100-year storm hits, the modeling indicates the UK could see around 6 massive supergrid transformers in England and Wales, and another 7 in Scotland, completely damaged and taken offline.
13 massive transformers destroyed.
And you can't just run to the hardware store to replace a supergrid transformer. They are custom-built behemoths that require specialized heavy transport just to move them.
Replacing 13 of them, assuming you somehow have the multi-million-dollar spares just sitting there ready to go, takes anywhere from 8 to 16 weeks.
Best case scenario.
You are looking at months of rolling blackouts and power rationing to replace critical nodes of the national infrastructure. The economic downstream effects of that are staggering.
But grid operators aren't just crossing their fingers. National Grid in the UK actually employs a robust defense strategy.
They do. They are quite proactive.
They utilize a specialized forecasting tool called MAGIC, which was developed in partnership with the British Geological Survey. If MAGIC indicates a severe geomagnetic storm is imminent, grid operators don't unplug the system to hide from the surge.
They enact an all-in policy.
Right, which sounds paradoxical, to bring more equipment online when facing a massive electrical surge.
It does sound completely backwards.
But their strategy is to switch on all available transformers and instruct standby generators to start pumping power into the grid.
The goal is to spread the massive induced electrical load as widely as possible across the entire physical network.
Sharing the burden.
Exactly. By lowering the resistance of the overall system and sharing that burden, they reduce the localized strain on any single vulnerable transformer. It is an active, dynamic defense.
It is a phenomenal operational mitigation. But terrestrial power grids are just one layer of the onion. If we look at the communication networks binding the global economy together, we find vulnerabilities in entirely different environments.
such as the ocean floor.
Right.
Right.
So if the power grid on land is that exposed, what happens when we look at the infrastructure hiding at the bottom of the ocean? You might naturally think that submarine communication cables are perfectly safe.
Because we use fiber optics for the internet backbone now.
Exactly. Fiber optics transmit data using photons of light, not electricity, which means the glass fibers themselves are completely immune to magnetic fields. So we're safe, right?
What's fascinating here is the ultimate irony of our modern light-speed fiber optic internet. Its survival depends entirely on 19th century copper wire technology dragging along the ocean floor.
How so?
While the glass fiber is immune, a light signal traveling across the bottom of the Atlantic Ocean naturally degrades over that distance. It needs to be amplified.
So they use repeaters.
Right. Distributed along the ocean floor are optical repeaters, and those physical repeaters require electricity to function. That power is supplied by long, continuous copper wires running completely parallel to the fiber optic cables.
Which essentially turns the entire transatlantic internet backbone into a gigantic antenna for space weather.
That is exactly what happens. During the massive geomagnetic storm of March 1989, the very first transatlantic optical fiber cable, TT8, experienced induced potential shifts of up to 700 volts.
700 volts on an optical cable.
Now, the system's power supply was robust enough to handle that specific voltage drop and maintain the connection. But it explicitly proves that our seemingly untouchable fiber optic network is firmly tethered to highly vulnerable physical conductors.
And if we move from the ocean floor up to low Earth orbit, the environment becomes an absolute gauntlet. There are thousands of satellites currently in orbit, sitting completely outside the protection of the Earth's atmosphere.
Directly in the firing line.
So what are the specific threats up there?
Satellites face two incredibly complex physical threats from the radiation environment of a superstorm. The first threat comes from electrons.
Okay, the lighter particles.
Right. Low-energy electrons cause surface charging, where static electricity builds up on the exterior panels of the spacecraft. But the far more insidious threat is internal charging.
How does that happen?
This occurs when highly energized electrons, specifically those exceeding 100 kiloelectron volts, physically penetrate the outer hull of the satellite.
They punch right through the metal.
They punch through and bury themselves deep inside the plastic insulators like Teflon and Kapton, and within ungrounded metal components right next to the critical processors.
They act like microscopic time bombs, just sitting there, accumulating a negative charge over hours or days until the voltage differential is so high it finally arcs.
An electrostatic discharge. A literal spark fires deep inside the circuitry.
And depending on where that spark lands,
It can send a phantom command to the satellite's thrusters, it can corrupt an entire databank, or simply fry a critical power regulator beyond repair.
and that internal charging is just the threat from the electrons. We still have to account for those solar energetic particles, the heavy SFPs we discussed earlier.
Yes. The heavy ions cause what engineers call single event effects. Imagine a single, highly energized cosmic ray acting like a microscopic cannonball.
It physically blasts completely through a microchip on the satellite.
As it tears through the silicon, it deposits a dense trail of electric charge.
And that microscopic trail of charge is enough to either flip a piece of memory from a 1 to a 0, what engineers call a soft error, instantly altering a critical line of code, or cause a hard error, where the energy burns the logic gate out entirely.
It just destroys the hardware.
But I want to balance out the doom and gloom here, because human engineering is remarkably resilient when we actually understand the threat we are facing.
We do have mitigation strategies in space, too.
Yeah, the source material highlights a fantastic paradigm of active resilience. During a massive solar event in October 1989, the University of Surrey had an experimental satellite in orbit called the UOOSat-2.
Oh, the memory washing example?
Yes. This satellite was blasted by a massive wave of STEPs. It experienced an order of magnitude increase in bit flips in its memory. We are talking about 10 times the normal amount of radiation-induced errors, actively shredding its operational code.
But the satellite survived.
It stayed fully operational. Why? Because the engineers didn't just try to shield it physically. They built an automated memory washing algorithm.
It is a brilliant software solution to a physical hardware problem.
How exactly did it work?
The satellite had a background daemon constantly reading its own memory blocks, calculating checksums to find the corrupted ones and needs, and actively rewriting them back to their correct state.
So it was an automated arms race.
Scrubbing the errors out of the system faster than the solar radiation could flip them?
So what does this all mean? When you synthesize all the data in this report, the paradigm shifts.
Hmm.
Your highly connected, technology-dependent life sits inside a delicate, invisible magnetic bubble.
A bubble that we take entirely for granted.
And every century or so, that bubble gets violently peeled open and battered by the sun. But we are far from helpless victims of the cosmos.
We are learning.
By deeply studying historical anomalies, utilizing active software defense like the UOSAT-2 memory washing, and constantly monitoring the physical grid with tools like magic, we are actively learning to engineer our way through the storm.
This raises an important question, though, regarding the stark limitations of our current forecasting capabilities.
We aren't as prepared as we could be.
No. We have these incredible mitigation tools on the ground, but our situational awareness in space is severely restricted. We can see a flare flash, we can watch a CME launch from the sun, but we largely issue general probabilistic warnings.
We don't have the precision of terrestrial weather forecasts.
We completely lack that precise, localized lead time. We cannot tell a national grid operator exactly which coastal transformer will take the brunt of the induced current or precisely what minute the voltage collapse will begin.
And that leaves you with a final, lingering thought to mull over. Right now, our primary early warning system relies on a solitary satellite situated at the L1 Lagrange point.
A gravitationally stable parking spot about 1,000,000 miles out toward the sun.
That single satellite is our buoy out in the cosmic ocean. It is the only physical instrument we have that can measure the actual magnetic orientation of an incoming CME and confirm whether the field is pointing south.
The crucial variable.
But because of its proximity to us, that satellite gives us a mere 15 to 30 minutes of definitive warning before the plasma physically slams into the Earth's magnetosphere.
Just 15 minutes.
I want you to imagine being the grid engineer staring at the telemetry monitor in a national control center. The vertical magnetic field data drops completely south. The alarm sounds. You have exactly 15 minutes to make a monumental decision.
The weight of that choice is staggering.
Do you plunge millions of people, emergency services, and financial centers into deliberate darkness by manually shutting down the national power grid to save the physical transformers? Or do you gamble that the infrastructure can absorb this surge?
A terrifying gamble.
And you have to make that call based entirely on a single stream of data, beamed from a solitary satellite floating 1,000,000 miles away in the dark. Keep learning and keep looking up.